For our second short lecture on cosmology, we want to look at gravity because gravity turns out to be the key. We talked about, the basic ideas that Newton had and gravity, and his ideas that in order to be stable, the universe had to be infinitely large and infinitely old. That turns out not necessarily to be the case. To really understand the universe, it became very clear you have to understand gravity. Well, in the early 20th century, it became very clear that to understand gravity, you have to understand general relativity, because gravity alters space and time. We talked about this in our lectures about black holes, that relativity is what you need to understand and how it works, because it stretches space and time. Otherwise, black holes don't make really any sense. And so gravity alters space and it alters time. So you have to understand the nature of general relativity. So Einstein works out the basics of general relativity early part of the 20th century. And so he publishes this. And so not long after he publishes about general relativity, which describes how space is stretched by gravity, that became obvious that using his equations for how space is stretched, it ought to describe the universe as a whole, because the universe is basically space with stuff in it. We know the space is stretched. We talked about this back when we talked about in general relativity before, because of gravitational lensing, that something has a lot of gravity and it bends light, and so light always travels the shortest path, so that would say it's also bending space. And so we have evidence of gravitational lensing. Again, we talked about this before. We have evidence that light is being bent, therefore space is being bent or distorted. So Alexander Friedmann takes Einstein's equations, okay, and works through these equations. Again, Einstein publishes special relativity pretty early in his studies here. It took a number of years until he had worked out the details of general relativity, because it's way more complicated. It involves a level of mathematics substantially beyond the level of this class. But it's his field equations, which actually have things called tensors in them, which are kind of like vectors on steroids. But these tensors, the field equation with tensors, can be kind of simplified down in certain circumstances. Alexander Friedmann worked through the mathematics here and published a paper in which he looks at the nature of space in the universe. And so the equation here we call the Friedmann equation. And so the left-hand term of the Friedmann equation here basically says the rate of change of space, that's what the R with the dot on top of it means, rate of change of space divided by the size of the space. So this is a term that's a proportional change in space squared, minus 8 over 3 pi g, those are all constants. G is the universal gravitational constant, so that relates to the nature of gravity. The thing that looks like a P there, that's rho, a Greek rho, that is the density of the universe. And so the denser the universe is, the more gravity has an impact on it. Well, duh, that kind of makes sense. Okay, the less dense it is, the less stuff that's in the universe, the less gravity has to do with it. And the right hand term, those are all, on the top are constants. K is a number, it's 0, 1, or minus 1. C squared, speed of light squared, and then R is basically a scale factor for the universe. And so we have here this equation. Turns out the equation is very complicated, unless it's empty. If rho is 0, in other words, if there's nothing in the universe, this is actually a pretty simple equation to solve for someone who knows differential calculus. It's what we call a differential equation. So you take calculus 1, calculus 2, calculus 3, and then differential equations in the next class. And that's where you learn to solve that equation if there's no rho in it. With rho in it, it's a nightmare to solve. And it turns out that these differential equations have some interesting properties. We don't exactly know rho, the density of what's in the universe. So that means that when we try to solve this equation, we end up with sets of solutions. We also don't know exactly what k is. But one thing that does happen in this equation is that there's basically two sets of equations, or two sets of solutions to the equation. So depending on what rho and k are, then, and k is actually sort of determined by what rho is, then what happens is that there's two possible types of solutions. One type of solution is a universe that's always expanding, and the other type of solution is a universe that's always contracting. So the universe either expands or the universe contracts. It's not steady. This flies right in the face of what Isaac Newton had always assumed, that the universe is static. This is something that physicists and cosmologists have thought since Newton's time. The universe is going to be static. And all of a sudden, we now have a universe that's not static. And this was a huge slap in the face of everybody that was a cosmologist at the time. And so this was just a huge thing. And then Albert Einstein himself didn't accept the solution. He said, oh, no. I can't accept that solution at all. Because that would make the universe, finite, or something. I mean, contracting doesn't make any sense. I mean, infinitely old, but it's dying, and it has an end. Expanding would imply it had a beginning. And so he didn't want to deal with that sort of universe. He wanted a universe that was pretty much static. So what happens in these equations is sometimes you can take a differential equation, stick a constant in it, and it doesn't change anything. So he sticks this constant in there to make the units work out properly in the equation. He has to have the constant as 1/3 times the constant times the speed of light squared. So that weird upside down v thing in the equation is actually a capital Greek lambda. And so he calls this the cosmological constant. And so you put this thing into the equation, the math works out so that you have a possibility of the universe being static. So you have rho and k adjusted to make the universe contract, and then you stick the lambda in there, and it balances that out and makes the universe static. And so the universe is now stationary, just sitting there, unchanging pretty much. So he sticks that into the equation, and everybody's, he thinks he solved the problem. Sticking a fudge factor in the equation is how they discovered neutrinos. Turns out there are neutrinos. So this seemed like a strategy to solve the problem. Problem was, if you remember, all these little spiral nebulae things out, and they were studying them, trying to figure out what they were. Some astronomers thought they were part of our galaxy, some Vesto Slipher, as we've said multiple times, Vesto Slipher discovered that these things are all pretty much redshifted, many of them very redshifted, and he was starting the idea of studying them to see what was going on, and this is where he thought they were actually outside the galaxy moving away from us. And that this led to the giant debate between Curtis and Shapley, where Curtis accepted that these things were like island universes, galaxies like our own Milky Way, except far away. And then Shapley said, oh, no, the Milky Way is the whole universe. Edwin Hubble then comes along, and he and Lemaitre both discovered that we have this expanding universe. And so they independently of one another measure galaxies and find out that the more redshifted they are, the farther away they appear to be. And so they come up with this relationship that for a long time was just called Hubble's law. We now call the Hubble-Lemaitre law. Okay. And so that was the consequence of this. And so discovering it led to the realization that the universe is actually expanding. We've already talked about it. So Einstein's response here was, wow, okay. Yeah, oops, wait. I mean, that would mean there's no cosmological constant. And many books say that he called it his biggest blunder. And so he actually travels all the way from Germany to Mount Wilson Observatory, meets with Hubble, and finally, then goes back to Europe, meets with Lemaitre, and then accepts that the universe is expanding. And so he actually says, okay, Friedmann was actually right. There is no cosmological constant in there, and so forth. Now, the idea that he called it his biggest blunder actually is a little bit suspect. He doesn't normally talk in that way about his work. He does admit that the cosmological constant probably should not have been in there. But as far as blunder, no, because that was really a legitimate strategy to put something in there, given the circumstance that he actually thought the universe ought to be static. And so that's really not so much a blunder as just simply a theoretical error. The idea that it's a blunder actually comes from another physicist, George Gamow, who was actually noted for exaggerating many things. He was kind of a jokester. He also just exaggerated many things. He used to, long after Einstein had died, he used to talk about how he and Einstein used to share coffee and discuss things. And while they were talking one day, Einstein told him that the cosmological constant was his biggest blunder. That's important to Gamow, because his theories of cosmological expansion had no cosmological constant, and so he was like trying to make it out that Einstein admitted that Gamow was a better physicist than he was. Well, it turns out that as far as them actually meeting and having coffee on a routine basis, since they lived in different cities, hours and hours away from each other, and rarely saw each other except at a conference every few years, that was actually very unlikely that this conversation ever happened. So probably Einstein never called it his biggest blunder, though your textbook does do this. There's no evidence Einstein ever said that, other than Gamow saying that Einstein said it to him over coffee one day. And since Gamow is maybe not trustworthy in that particular regard, then I would say that maybe we ought to consider that he didn't really say that. At any rate, the basic concept is the universe is expanding. It's moving away from each other. Pretty much like raisins and raisin bread. The galaxies are staying put, but they're getting farther apart because space is expanding, because the Friedmann equation says space either expands or it contracts. It's not going to be steady. The Friedmann equation comes from Einstein's field equations that describe how space is affected by gravity. That is the key to understanding how the universe works. Okay. So what does this mean? The universe is expanding, but it does it on large scales. Space doesn't expand very much. So that means you had to have a whole bunch of space in order to notice the expansion. On small scales, like in the solar system, the space between the sun and the earth is not big enough to make the distance between the sun and earth get bigger. Gravity still wins there. The sun's gravity keeps the earth in orbit. You're not getting bigger because the universe is expanding. If you're getting bigger, it's because you're eating too much. But it's not because the universe is expanding. Earth is not getting bigger. Earth's not getting farther than the sun. Galaxies are getting farther from each other because the space between galaxies is huge. And this would be on a very big scale. Even the local group, gravity wins. But between the local group and the next big group of galaxies, in the local supercluster, the space between the clusters is so big that the supercluster is expanding. So it has to be at a big scale that you even notice this effect.